Hello. Welcome back, guys. So we're going to continue working or looking at evolution a little bit more and how scientists measure whether evolution has happened or not. So we've gone over the agents of evolutionary change, right? We said that they were mutations, gene flow, non-random mating, genetic drift, and selection. So these are things that drive evolution to occur. So a few basic concepts before we get into what Hardy-Weinberg equilibrium is, which is this concept we're going to talk about with this lecture. Basically, you need to understand the population is a localized group of interbreeding individuals. So human population, we interbreed, is localized to a certain area. The gene pool is the collection of all those alleles in the population. So all the brown hairs, all the blonde hairs, all the black, and so on. Remember the difference between alleles and genes. Alleles are an alternative version of a gene. So there's the gene for hair color, and alleles for the genes of hair color is blonde, brown, black, red, and so on. So alleles are the alternate versions of the gene. Now this next term is the allele frequency, which is how common that allele is in the population. Meaning, is A more common than big A is more common than little a. Like big A occurs in 80% of all the alleles out there, whereas little a is only 20%. That's kind of what allele frequency refers to. So, when looking at evolution of populations, evolution is a change in those allele frequencies. So that's how we know evolution has happened. If there is a change in the allele frequencies, is there a change in the amount of big A's and little a's? So what scientists did is they came up with this, what's called a null hypothesis. Basically, what would happen if allele frequencies did not change, or what would need to happen to cause the allele frequencies not to change. So how to stop evolution. So scientists basically came up with is these qualifications. First, it needs to be a very large population size, meaning that so that no genetic drift can happen. No migration, so that means there's no gene flow in or out of the population. Right, so there's no one coming in and going out. No mutation. Random mating, meaning there's no sexual selection. You mate with random people. And then there's no natural selection. Everyone is equally fit for that environment. So again, this is hypothetical. These are things that need to happen for evolution to not happen, if that makes sense. So again, what would cause allele frequency not to change, i.e. what would stop evolution? And these things would need to occur for evolution to stop happening. So those are very important. Again, you guys should be familiar with these. Just think of the agents of evolution. You guys know those, or should know those. So no genetic drift, no gene flow, no mutation, no there is random mating and natural selection. So those are kind of the things that need to occur for evolution not to occur. So here comes this Hardy-Weinberg equilibrium. Basically, we wanted to find a way to measure evolution quantitatively, meaning using numbers. So Hardy-Weinberg, these two scientists came together and kind of came up with this model. Again, what would happen if there was no evolution, which is what a null hypothesis is. It's what would happen if this didn't happen, or what would need to happen if this didn't happen. So what would need to happen for evolution not to happen? I know it's a little confusing. So first off, they're rarely ever in this ideal equilibrium. So they're very rarely do natural populations have this happen. But it's a useful model to measure if forces are acting on a population. So we're first going to look at the equation by counting alleles. So assume that there's 2 alleles in every gene. So there's two alleles, whether it be tall or short, wrinkled or smooth, whatever it may be. So we're going to refer the dominant allele, which in this case is big B, as the letter P. Okay, so letter P represents the dominant allele. The recessive allele is represented by the letter Q. Okay, and in this case, the P and the Q, when added together, will equal 1. That makes sense. So again, frequency of the dominant allele. So when we're talking about frequency, it's the percentage. So let's say 80% of all the alleles in the gene pool are big B. That would mean this P, the number would be 0.8. Okay, so if this is 80%, so if there's 80% of the population is big B, is made up of big B's, then this, of course, would be 20%, or 0.2. So 0.8 plus 0.2 equals 1. This might be a little confusing. Listen to this now. We're going to do lots of problems, and it'll make sense to you once we get the problems. So don't do too much freaking out. Now, when we want to count individuals, i.e., how many homozygous dominants are there? How many homozygous recessives are there? How many heterozygous people are out there? This is how we figure that out. So if you have P of a homozygous individual, that means they're big. That means you would need to find the frequency of big bigs in a population. You need to multiply P by P. To find homozygous recessive, it'd be Q times Q. And frequency of heterozygotes would be 2PQ. Okay, so let's say hypothetically, my P frequency is 0.3. Okay, so 0.3. So 0.3 times 0.3 is 0.09. So that's 9% of my population is homozygous dominant. Which means if this is 0.3, this is 0.7. So 0.7 times 0.7 is 0.49. So 49% of the population is homozygous recessive. I know it's hard because I can't do the numbers, but trust me, when I show you this, it's not that hard. It's pretty easy, actually. So this whole equation needs to add up to 1 as well. So this represents the homozygous dominant, this represents heterozygous, and this represents homozygous recessive. All right. And again, this whole formula is trying to find the frequency, the percentage of big B's in the population, or big B, little b's in the population, or little b's in the population. So, hypothetically, you had 100 cats, 84 black, 16 are white. How many each genotype? So that means you're trying to find how many homozygous dominant, homozygous recessive, and heterozygous individuals. So, first of all, we know from this that 16 white individuals. We know white's recessive, so in order to be white, you need to be little b. So from this, we can figure out, okay, that means that Q squared is 0.16 because it's 16 out of 100. So it's 16% of the population is white. Okay, so from that, we can say, okay, well, what's Q going to be? Well, we could just square root 16 and we get 0.4. And then once we have what Q is, we know what P is because 1 minus 0.4 equals 6. So for you people that aren't very good at math, this is probably going to be confusing. Probably if you're even good at math, it's confusing. We're going to be doing this multiple times in class. So make sure if you still don't get it after that, let me know. So this is the type of problem you might get on a test. Is basically I give you this information. I say that white's recessive, and then you need to figure out, well, what's P, what's Q, and so on. you would need to figure out these numbers. That's kind of the goal. So in science, we will go ahead and look at this and say, oops, we will go ahead and say, okay, this is assuming Harvey-Weinberg equilibrium. But then the actual data came up different. So that basically tells us, well, there's something that's happening that's making the homozygous dominant more common than the heterozygous individual. So that means this must be being selected for. Okay, that's it for right now. There's the third part I'm going to make as homework because this is getting too big already. Third part we're going to make as homework probably tomorrow or Wednesday night. All right, you guys have a great night and come in tomorrow with questions. Talk to you later. Bye.